This video is going to demonstrate the exploit of SurgeMail version 3.8K4-4. This version has a vulnerability that made it improperly handle long list commands, which results in a stack overflow that allows an attacker to execute the code remotely. The first step is to determine whether or not a vulnerability exists in the application, and this is done through fuzzing. The book provides the code written in Ruby, and the file is saved in the .msf4 modules auxiliary fuzzers folder. We are now going to look at the fuzzer code. The fuzzer module imports the IMAP and the denial of service mixins. SurgeMail requires authentication, and IMAP will give us that functionality. The fuzz string is set as a randomized string of alphanumeric characters with the maximum length of 1024 bytes. Next, we see where the fuzzer connects and logs into the remote service. If it fails to connect, breaking the loop, then this is something worth looking into. The server's lack of a response is an indication that we have successfully caused an exception in the remote service. The variable fuzzed is set to a random string generated by the framework. The malicious request is built by appending malicious data to the vulnerable list command. So if the fuzzer doesn't receive a response from the server, it will print out server crashed, no response. We are now going to test our fuzzer. First, we must attach SurgeMail to Immunity Debugger. And we need to make sure it's unpaused. And now we're going to go into Metasploit and load the fuzzer and run the exploit. We need to set the options. This is the password, the user, and the IP of the remote host. And now we're going to run our exploit. You can see the randomized string of characters being generated. And as we can see, the server crashed. We're going to go in and we're going to look in Immunity Debugger, and sure enough, there's an access violation. This fuzzer crashes a program, however, it doesn't overwrite any memory addresses, which doesn't do us any good. So by sending a longer string, and the next time we're going to use 11,000 bytes, we should be able to overwrite the Structured Exception Handler, or SEH. The ability to control the SEH handler will make the exploit more reliable. In order to generate 11,000 A's, I've gone in and modified the fuzz string to read as follows. I've already attached SurgeMail to Immunity Debugger, and we are ready to run the exploit against it. And as you can see, there are a lot of A's, 11,000 to be exact. And the server crashes. We go into Immunity Debugger, and we do see there is an access violation. We are now going to look at the contents of the SEH chain. And we can see there are 41s in it, which of course are the uppercase A in hex. We are now going to follow the address in the stack to show the stack contents leading to the SEH overwrite. And this is found down in the lower right hand corner of the pane. Now we know we can control the SEH chain with an overly long buffer. Now that we know we can control the SEH chain, we need to determine the exact length required to overwrite it on the target. To do this, we are going to modify our fuzzer code to create a non-repeating random string of characters of a specific length, as I have done here. I have already attached SurgeMail to Immunity Debugger, and we are ready to run the exploit. And the server crashed. We now go into Immunity Debugger and we view the SEH chain to see where the target was overwritten. And here we see it's at 684E3368. We now use the pattern offset script to determine exactly where the overwrite occurred by passing it the characters of interest, which are the 684E3368, followed by the length of the string, which is 11,000 characters. We see the value of 10,360 is returned. This means the 4 bytes that overwrite the SEH are 10,361, 362, 363, and 364. Now we can change our fuzzer code one last time to verify these findings. I have modified the fuzzer string to reflect the following. It will build the malicious request beginning with 10,360 A's, hex 41, and then starting at 10,361 we are going to insert 4 B's, hex 42, which should overwrite the SEH, and then as a filler we will insert 636 C's. If you do the math, these add up to 11,000 bytes. We'll run the exploit against the target one more time to show we have entire control of the SEH chain. We can see the end of the 10,360 A's and the 4 B's that should be overriding the SEH, and then our filler C's. And the server crashed. We'll view the SEH chain, and it should contain our 42s or our B's, and it does. We'll now follow the address stack, and sure enough, the SEH was overwritten. We are ready to take over our target. There are some SEH restrictions we must overcome. There is very little space for shellcode following the SEH overwrite. Typically, a pop-pop return set of instructions would be used to reach the next SEH, followed by a short jump forward into the shellcode. The way to overcome this limited space restriction is to develop an exploit that will use as much space as possible for our final payload. Now that we are done fuzzing, we know we can control the SEH. It is time to develop the code that will run an exploit against the vulnerability we found. And when I say we, I am referring to the authors of the book. The tactic used is to overwrite the SEH with the pop-pop return instruction pointer. Once that is overwritten, a short jump backwards rather than forward will be made. Next, we'll use the space gained in the short jump to execute the large jump farther back into the NOP slide and shellcode. To ensure portability of the exploit across different versions of Windows, we will use a return address from SurgeMail's executable file. We will now review the code that will perform the actual exploit on the SurgeMail vulnerability. The space declaration refers to the space available for shellcode. This is important because it determines which payloads Metasploit will allow you to use when running the exploit. The return address is the address we acquire from SurgeMail's executable. To get this address, rerun the msfpscan-p command, which I'm going to demonstrate right now. And we are going to use this last address listed. In order to perform a 3-byte overwrite of the SEH, the 3 bytes are added to the targets block in Little Endian order. Endianness is determined by the target CPU architecture, and Intel-compatible processors use Little Endian byte ordering. It is this command that will ensure our exploit is portable across different versions of Windows. As with the fuzzer module, this exploit must also connect and log into the target. The buffer is filled with the NOP slide. The near jump sequence of instruction jumps backwards to a location near the beginning of the buffer. The next SEH instruction makes a short 5-byte jump backwards. The EB is the operation code for the short jump. This code allows for more than 10,000 bytes available for our shellcode. The average space required for functional shellcode is less than 500 bytes, so we have plenty of room. Finally, Mr. Evil is built using all of our exploit components. There is one last thing we need to worry about, and that is bad characters. Bad characters can get mangled while being read by the application, which will render your shellcode unusable, which means your exploit won't work. So how do we get around that? We need to tell Metasploit to exclude them, which we have done here. Thank goodness the book gives us the bad characters to use. It is now time to run our exploit. Notice the added payload option. This will open the session on our target. I'm now going to run the exploit. Because the shellcode is regenerated every time an exploit is run, this will need to be ran several times before all the bad characters are finally ignored. I'm going to go ahead and pause this until I can get my shell. And success! I now have a shell into the target machine.